So we're going to kind of change gears a little bit in the course here. Look at this example to start off. So this graph shows the rate of change of megapounds of snow. What is a megapound? What's a megapound? 1,000,000 pounds. A megapound would be 1,000,000 pounds of snowfall in respect to time and elevation. So this is a contour plot. This is a multivariable function. Actually, no, it's the rate of change, right? So it's a contour plot of a multivariable rate of change function. Multivariable rate of change function. So this is different than, so we saw like rate of change of partial with respect to x, partial with respect to y, which was rate of change just in terms of one variable or one direction in the xy plane. Now this is kind of a different kind of rate of change function because it's given with respect to two independent variables simultaneously. Okay, so here's a warm-up, just using the plot. Interpret the situation for an elevation of 3,500 feet at 1.4 hours and 1.8 hours at an elevation of 5,000 feet. So what does the contour plot tell you about those two situations? So maybe take a minute to discuss that with the person next to you. Interpret this with a sentence, what the contour plot tells you about these two situations. Okay, go. With what?
I have to drive home where I need to drive.
Oh, okay. Did you hear that? So Tony, what do you think? For this first one, for part A, what did you come up with?
I mean, at elevation of 3,500 feet, 1.4 hours. The change of Z is, positive is passes, or it's also positive as you go higher in elevation.
And what is the value of the rate of change?
Maybe around 1.
Is it 1?
1.4.
Just 0.4, right? Is it 0.4? So 0.4. What are the units on that? 0.4 what? Megapounds per so it's per both, right? So this is the rate of change per both. So per 1,000 feet times hours. So it's megapounds per 1,000 feet per hour. So this is different than our partial derivatives, right? Partial derivatives just with respect to one independent variable or one combination of the independent variables as a direction, right? But now this is different. And then what was the other one? For 1.8 hours, elevation of 5,000 feet. 1.6? Again, 1.6 what? 1.6 megapounds per 1,000 feet per hour. So now I want to interpret those values. Can we apply, now that we've got this new kind of rate of change? It's still a rate of change. So can someone interpret this for us? What do these rates of change mean? Remember, we worked hard on this, right? Sam, was right?
Yeah, at an elevation of 3,000 feet and at a time of 1.4 hours,
Mhm.
the megapounds of snow varies by 0.4 megapounds with every small change in elevation and hours.
So for every small change in elevation and hours, the amount of megapounds of snow changes by 0.4. That's what I heard you say.
Yeah.
All right? Becca?
Would it change by 0.4 times dx and dy?
Okay.
Just small like change.
Yeah, you got to see. Well, so given variations, it's not that the change in megapounds is 0.4, but there you go. 0.4 times what? Yeah. Sam, finish it.
Times as much
As.
the megapounds as the elevation and hours change.
Right. So what would given any change in elevation and time, both from what? From 3,500 feet and 1.4 hours, the resulting change in megapounds would be, so we'll say dW is 0.4 dE or dt? Both, right? Both. Because the units on this 0.4 is per 1,000 feet per hour. So given any change in elevation and any change in time close to these, right? Close to 3,500 feet, or given any change in elevation and change in time from 3,500 feet and 1.4 hours, the resulting change in weight of snow would be 0.4 times both those changes. We could do the same thing with this. It'd be 1.6 times, but that would be for a different situation when the time is 1.8 hours and elevation 5,000 feet. Okay, so different kind of take on rate of change here. But then the same kind of interpretation because it is rate of change. Does that make sense? Okay, so let's warm up. Okay, so what I want you to do now is I want you to estimate the average rate of change of snow fallen from 1.4 to 1.8 hours and from 5,000 to 6,000 feet. The average rate of change is like an equivalent constant rate of change over that region in the contour plot. So from 1.4, what did we say? From 1.4 to 1.8. And from 5,000 to 6,000 feet. So in that time and elevation range, the rate of change varies. But if you were to come up with one kind of like approximate rate of change for that elevation range and time range, what would it be? So if you just kind of right? So it's kind of like this is like a dt of what, 0.2 and a de of 1. And I want to know I want to make an approximate for like what was the weight of snow fallen over that elevation range and over that time and hours. That change in time and hours. Well, I would need a single rate of change, right? So we need a single rate of change for that. What would you say? Would you say 0.2? Would you say 2.2? So what would you estimate for that rate of change for that time interval and elevation interval? What's that? He wants 1.5. So it's just we're just kind of eyeballing here. It's like, all right, well, on this corner it's what? 2 here. On this corner it's about 1. So is that where you came up with 1.5? Yes, he just kind of the average of, because it's changing across this diagonal, right? So he went somewhere between 1 and 2 is 1.5. You could also like go right to the center. Another way to do it is go right to the center of it and pick off the rate of change right in the center. What's that? Like 1.6. Okay, so we're just eyeballing, right? So any estimate around 1.5, 1.6, 1.4 would all be legitimate. And so then estimate the amount of snow fallen would be about what? In that time interval and that elevation change. Nick, what would you say?
It'd be 1.5 1, so we 1.5 times 0.2.
Right, so given their two changes in our independent, the change in the weight would be the rate of change times those two changes. So is that 1 times 0.2?
Yeah, which we get 0.3.
So about 0.3 megapounds of snow. Good or bad estimate? Why bad? Why? Because there's a great variation in rate of change across this, right? And we just picked one rate of change for these like kind of these large changes in our variables. We picked one rate of change to be constant for that whole thing. So that's a pretty big assumption, given such a greatly varying rate of change across those intervals. Does that make sense? Yeah.
Wait, it says it's from 1.4 to 1.8, so isn't it 0.4 instead of 0.2? Or minus something?
Oh yeah, it should be 0.4. Thank you. Yeah.
Yeah, it's 1.4.
So is that 0.6?
Yeah.
It's my first mistake in 20 years of teaching. So no wonder you didn't say anything. I'm being sarcastic. I make mistakes, guys. If you're uncomfortable, then speak up. Okay. 0.6. Are we better now? Okay. This should be 0.6. No. Oh, I have it right now. I changed that? I have it right now. Okay. DW is 0.6. Okay. Cool. So we said this is kind of a crude estimation. Why? Because in those intervals of time and elevation, the rate of change varies greatly. There's lots going on with the rate of change there. And just to assume one rate of change over that whole thing is a very crude assumption, right? It's not going to be precise. So how can we make it more precise? What could we do to make this better? I want to get the change in weight of snow across this time interval of 0.4 and this elevation interval of 1,000 feet. Yeah, Ronnie.
Summation of all the changes.
Okay, and when you say all the changes, which?
The box you created, all the changes in there, just summation of them.
That sounds like a lot. Are you saying, I mean, how many rate of changes are there in there? Like infinite, so it's like an infinite number, right? So I just want to, maybe it's still going to be an estimation, but something I can do by hand that would be a better approach or a more precise than this. So what can I do that's still like we can get it done in the next 5 minutes, will be better than this? What could we do? And what does that mean? Yeah, so when you say Riemann sum, what does that mean? So in this situation, what do you want to do? What's that?
Pick a couple points.
Pick a couple points. Okay. So like here's a point and here's a point. So what do you mean? What's the problem? I'm picking one rate of change for this whole big change in t and this whole big change in elevation. So how can I do better? Yeah, Chris?
Well, then see if you find like the rate of change at the beginning and the end, and like average.
Well, that's still just getting, that's kind of what we did, right? That's still just getting one rate of change for this whole big interval. Sam?
That's kind of like what we did, right? We have one rate of change for a big interval, so we want to decrease our interval.
Okay. So what does that mean in this situation? Decreasing the intervals. Emily, do you have an idea? Right. Right. So let's break this up. Instead of doing one big box, let's do 4 smaller boxes, and then do an eyeball a constant rate for each of those. So now just focusing on this little box, what constant rate might be a good estimate across those changes? And what one rate might be a good one rate of change to estimate across those? Okay, so your task is to get, based on that approach, 4 smaller, we're going to call these dA kind of like a little change in area. But a dA consists of a dt and a dE. So for each of those 4 little dAs, you're going to come up with a constant rate and then do another estimate for the same thing, the amount of snow over the 0.4 hours and the 1,000 elevation. Okay, so I'll zoom in on that so you can see it better. Oh, I'm taking attendance, okay? So, is the task clear? Do you know what you're after here? So 1.4 to 1.8 and 5 to 6. Do I have the right box here? I didn't want that. Okay, but now going from 1.4 to 1.8, 5 to 6,000 feet. But you're going to break it up into 4 subproblems, right? Trying to get more, we're getting a more precise way of calculating this, or getting a better estimate for the weight of snow falling in that time interval and in that elevation range. Go, work together. Okay, so how did we do this? Veronica, how'd you do this?
Oh, so we just took rate changes from tiny split boxes.
Okay, and what'd you say they were?
For the top left, we said 1.5
So you said 1.5 from 1.
for that.
Okay,
And then on the top right, we said 1.8.
okay,
Bottom left, 1.3, and then 1.6. And then we did each one by 0.5, so that's the change of, what is that? Oh, the elevation.
right,
And then 0.2 for the change in hours. Those
Okay.
were four originally.
all right, so the whole thing looks like what?
The rate times 0.5 times 0.2.
Okay, so first of all, these rates, did the rest of you get something similar to those? I see some nods. Okay, good. All right, so then, so you did 1.5 times 0.5. Now the change in elevation is 0.5, and the time in hours is 0.2. And then, what after that? Somebody take over from here. What will I do next? Yeah, Nick.
I would take the one on right below 1.3.
Okay.
So add 1.3 times 0.5 times 0.5 times 0.2.
So we add them all up. Is that right? We're just going to add up now the changes in weight from each quarter of that original thing. and then 1.8 times same thing, plus, and what do you get? What's that? 0.62? So the rest of you use different rates. Did you get something a little bit bigger than 0.6? 0.615? Yours was less than 0.6?
I got 0.615.
But it was bigger than 0.6?
Yeah.
Yeah. Because our first estimate was 0.6, so now we're getting something a little bit bigger. So hopefully in theory, that's more accurate, right? And that's more accurate because we've broken this up a little bit more. So 0.62, what's the units on that? Megapounds per elevation per, or, nope. This is megapounds, right? This is our estimate for the change in weight, right? Because we're multiplying the rates times the little changes, and that's just going to give amount of snow fallen or approximate over that time frame and that elevation change. Okay? So now I want, and so we could organize that as what? As like summing across the rows. So like what would that be? We'll just do it. So you can arrange that as like what? Like this is would be summing up this column and then summing up the second column, right? And then this whole thing is what, like a sum of the columns, right? So this whole thing would be then adding that plus that would be summing up that column plus that column. You see that? Okay, that's something to just keep in mind as a way to structure that, summing that. So let's put this back and let's ask another question here. Okay, we did that. So now I want you to write an expression that would represent the same total weight of snow, but this time using 1 billion subrate regions. Same weight of snow. So how much time do we have left? 9 minutes. Can we do 1 billion in 9 minutes?
Everyone does 10 million each.
Okay, yes, Richard, thank you. That's teamwork makes the dream work, right? So what does that mean? 1 billion subregions. So like, so I'd have to. So thinking about what we did before, it's like I'd have to sum up. I'd have to sum up what? A rate of change times dE and a dt. Like, and we could do it across the columns like that, sum up all those columns, and then we could or sum up the boxes in each column. I have a whole bunch of those, and then I could sum up all those columns across this way, right? And so it's the idea of a double sum. And how about our estimate then? Good or bad? Yeah, better. Yeah, way better, right? So if we had 1 billion, it'd be we'd be converging on what the actual amount would be, very, very close to the actual amount of snow. All right? And so a double sum as number of boxes gets really big. Could be rewritten how? We've seen this before, or in Calc 3.
You can write it as a double integral.
Double integral, right? Double integral. And so it'll be the double integral from, so what did we say? We were going to add up the e's first. So that would be from 5 to 6,000 feet. And then from 1.4 to 1.8 hours of the rate of change function. I guess I didn't define that. So rate of change of weight with respect to E and T Oh, sorry, it's off the screen. So this is the rate of change of weight of snow with respect to elevation and time, and then times, yeah, it's a DE first, right? And now this would be this would represent that exact weight of snow over that time interval, over that elevation range. Okay, so this is, again, this is what representing like a gazillion little squares, right? Summing up, like finding the rate for an itty bitty square, or basically like a point, the rate at a point, times a little, like I said, dA, which is like a little infinitesimal square, or square element. It consists of a super small dE and a super small dt. But like we started off the class saying, it's just that rate times a little change in E times a little change in T that gives you the amount of snow for that change in E and that change in T. But now now those changes in E and changes in T are just really, really small. Okay, so let's look at what would this mean instead of a contour plot like this if our rate function was a surface. So what would that, let's go back to the 4, we're going to go back to the box of 4, the 4 boxes. Okay, and so I've got, what is that? So this is, say, going to be my time in hours. It's my t-axis here. And this is my elevation. So this surface is the rate of change, okay? This is the rate of change of weight with respect to time and elevation. So it's not the amount of snow. So what was I saying? I was going from, T was going from what to what? 1.4 to 1.8. And elevation going from 5 to 6. Nice and big. Okay, so there's that same square right here, right? It's from 1.4 to 1.8 this way, and from 5 to 6 this way. And so what do we do in each quadrant there? In each quadrant, we multiplied the rate of change, R sub W, times a dE, times a dt. What would that be? What would be the geometric analogy to that? So the rate of change of W is what dimension here in this? What dimension is that here? So this is our dE, right? No, det. And this is our dE right here. Where's the rate of change of W? The z coordinate, right? It'd be like the z coordinate. So it's like, so the rate times dE times dt is, in a geometry sense, computing what kind of thing? It's like a volume, right? Do you see that? That's like a volume of a rectangular prism. It's not the worst. Not the best. The height, this is the height, right? Height times area of the base. So it's that little estimation of an amount of snow fallen in the R3 sense, where the surface is the rate of change, that little amount of, or that approximation is the volume of a rectangular column, call it. Okay, so now when you do these rectangular columns, in terms of estimating the rate of change or estimating the height of the surface, the most common thing to do would be choose a corner and pick off the rate at a corner. So like for this first lower left quadrant here, this is lower left. This is lower right for this box. This is upper left. This is upper right. And now everything gets turned in R3, right? So where is the lower left here? Where's the lower left? It's here. Do you see that? That's the lower left corner. Got to be careful, right? Because that looks like kind of like upper left. But this is the same as the lower left. So lower and left and upper and right are with regards to the normal view of the XY plane. Do I have it right? Is this lower left? Oh, I've got the wrong one. So I'm sorry. See how confusing it is. So I'm showing this one on the picture. Is that right? Is this the box that I drew with the red box? Okay, so this is lower left. That was an eraser. This is lower left. This is lower right. Upper left, upper right. So lower left, what's this? Lower right, upper left, upper right. Because they're going to say, estimate the value of the function, the value of the surface, using upper right corners. That means you're going to pick, to make the height of this thing, you're going to use that corner there, find the value of the function, and that will be the height of that rectangular prism for that whole DA, or that whole rectangle. Does that make sense? Okay, so there's like the rate of change interpretation of this, and then there's the geometry rate of change of this, where you're adding up these rectangular columns.